Hello friends, welcome to my channel. Let's have a look at problem 433, minimum genetic mutation. In this video, we're going to share two solution formats based on breadth-first search. First, I'll read through the statement to digest the problem requirement, and then we make a connection of this problem with the graph problem, and then we share the codes. First, the statement. A gene string can be represented by 8-character long string with choices from A, C, G, T. Suppose we need to investigate a mutation from a gene string start to a gene string end, where one mutation is defined as one single character changed in gene string. So here is an example in which we change the last T to A. So there is also a gene back called back that records all the valid gene mutations. A gene must be in the back to make it a valid gene string. So given the two gene strings start and end, and the gene back, return the minimum number of mutations needed to mutate from start to end. If there is no such a mutation, return -1. So here is a note which is important. Note that the starting point is assumed to be valid, so it may not be included in the back. So here are several examples, so you can interpret the output 1, 2, 3 in these three examples. So before we look at the code and analysis, let's look at the constraints, which is very important. So the start and end both have length 8, and the back has length bounded below by 0 and bounded above by 10. So this actually roughly gives us a problem size. So each of the string in the back actually has a length 8. Start, end, and back I consist of only the characters A, C, G, T. So these are the constraints for this problem. So in particular, the string length and the back length, so bounded less than 11. So here for this problem, our treatment will be based on BFS or based on BFS. So we could regard this problem as a graph problem. So here the identification is like this. Let's assume the graph is V and E. So V is the set of vertices and E is the set of edges. So here let's specify what's the node. So in this problem, the node is a valid gene string. So start is assumed to be valid, while end may not, right? So this is one part. So that's about the identification of the node. And the edge is the following. So there is a undirected or bidirectional edge between two gene strings if they differ at only one position, right? So once we transform the problem as a graph problem, or we identify the problem as a graph problem, then actually we just need to find the shortest distance from start to end in the sense of this problem. So this is very straightforward. So because for this we can use different ways to treat the problem. So for example, breadth-first search, because it's related to shortest distance, right? So with that said, we are ready to look at the code. So for the code, actually it's sort of standard. So here we are going to give two formats of breadth-first search. So taking slightly different thought process. It's good actually to know different formats of the same idea so that we can know how to implement in different situations. So first, let's look at solution V1. So in this case, so I'm going to do replacement in the string. So so here I'm going to use iterative format of breadth-first search. So originally we want to use a queue. So the queue actually will start things like start, at the distance or edit distance, so to speak. So distance with quotation mark. So from the start. So originally start is 0, right? So here what we put in the queue is nothing but gem, valid gem, and distance. So the distance is not in a very strict sense. So once we got this, then we can use a set visited. So this is just for avoiding repetition. So the back here given is a list of strings. So actually, in order for the ease of check, so I'm going to convert the back to be a set. So, and then we can do the standard while loop. So while q. So what we're going to do first, we get the gem, and then we get a step or distance, the q pop, right? And notice that we only put valid gem into the queue, right? So then first I'm going to check if gem equals the end, right? So this is the string matching. So if the gem equals the end, so we just need to return a step. Otherwise, so we want to add the current gem to the widget side. And then what we're going to do is that for each of the position in the current gem, we want to consider 4 possibilities of change. So we can use ACGT, right? So for this, let's see, for C in, I can use a string. So ACGT. And then we can actually replace each of position by the character C. So what we're going to do is for I in range. So as we know, the length of the strings is 8. So let's just write 8 here. So then what we're going to do is that, so we can make a new candidate. So we want to replace the character at index I with character C, right? So it's gem, so ending at index I. So this part can be empty if, for example, if I equals 0. So then we add this character, and then we consider from I plus 1 onwards. So this one. So for this one, we need two checks to make sure this candidate is a valid one. First, we want it to be a valid gem. In other words, it should be in the back to be valid. Another one is that it's the logic from the breadth first search. We want to make sure it's not visited yet. So this is if candidate in back and candidate not in visited. So in this case, so we're going to append this one. Notice that so there's one more distance, right? So we're going to use this candidate and step plus 1, right? So if we can arrive at end, in other words, we can mutate from start and then ending at end by way of the back, then there should be some number returned already. So if not, after the while loop, so we're going to return -1. So this is the full problem logic. So this forms a solution format. So let's do a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So with that said, so we finished the first version. Notice that in the first version, so we do replacement, and then check if the candidate is a valid gem or if it's in the back. So in the next version, we're going to do something slightly different. So what we're going to do is that we are going to, let's change this one to be V1, and then we change this one to be V2. So we want to traverse the back. The reason we can do this in this problem is that the back has a length bounded above by 10. In other words, the size is small. So for this version, I'm first going to define a isNeighbor function. So let's see, isNeighbor. So in other words, if the two strings of length 8 just differs at one position, right? So here I'm going to use S1 and S2. So this function is symmetric. For example, isNeighbor S1 and S2 equals isNeighbor S2 and S1, right? So what we are going to return is a sum of S1I does not equals S2I. In other words, the position where the two strings are different. So for I in range, so we can use any of this. So we need to assume that they are the same actually. So we want to check if this sum equals 1. So if it equals 1, it means they form a neighbor relationship. So with that said, actually we can do the breadth first search. So here we can think of we have a source and we propagate the source one layer and the other in a cascading way, right? So for this, first I'm going to initialize a result variable. So initially 0, and then we're going to initialize a queue. So and then visited is set. And then what we are going to do is that, well, queue. So for this layer of nodes, so we are going to push them to another layer, right? So the new queue, let's construct a new queue. So for all the elements in range length queue, right? So we need to do pop, right? So node equals queue pop. So what we want to do is that we want to find if there is neighbor of this current node in the back. If so, we are going to include those neighbors of this node, right? So we do this for every node in the current queue, right? So it's the current layer of queue. So let's see. First, we need to do a check. So we don't want to do extra work. We can regard this as an early stopping condition. So if node equals end, so we're going to return the current layer number. We can understand this result as a layer number, so which is also a interpretation of the mutation distance or the shortest mutation distance. So with that said, we can, because we have visited this node, we're going to add it to the set, right? So that is visited node, visited at this node, and then so here we are going to, in the first version, we for each of the gen, so we replace it in every possible position for every possibilities. And then for here, what we want to do is that we want to check the back to see if there are neighbors of this current node. So this is for S in back. So what we are going to do is that we want to check if neighbor. So if this node and S form a neighbor relation and S not in visited. So you see here again the logic is the same as above. Then what we are going to append, right, is but not a queue, new queue. Append is the S, right? So afterwards, what we are going to do, once we finished checking for the current layer, so we reset the queue to be the new queue, right? So once we do this, we need to, so the current result is the current layer for this state of the queue, and then we need to increment the result by 1. So we can actually understand this the meaning of this result variable as the layer number, right? So this way, once we finish this, so if nothing returned, so we are going to return -1 again. So this is the second format of solution. So from the point of view of breadth first search, so they are very alike, right? So they are the same in logic, but in representation format, they are different. So however, we've seen when we do the check of neighborhood, so the logic is slightly different. In other words, the direction is different. In the first version, we sort of doing in a brute force way by doing replacement. And in the second format, so we check or we traverse the back. for neighborhood check. So with that said, this is the second version of the solution. So now let's do a check. Yeah, it passes the first example. Now let's look at generic case. Yeah, it passes all the cases. So I guess that's about it for this problem. You are welcome to check out other videos in my playlist and in my channel. So if you have comments or if you have questions which you would like us to explain, just comment below the video. With that said, I guess that's about it for this video. Thank you.